Okay, so this is the chapter on equilibrium. This is chapter 7 in your book. So basically, we've seen principles of chemical equilibrium a few times in chemistry. You've seen it introduced in general chemistry, and you've probably seen it in analytical quantitative analysis. Basically, we know that thermodynamics can tell us whether a reaction should form products or not. It doesn't tell us about the rate or how fast a reaction will occur, but it will tell us that at a given temperature or pressure, should a reaction have a tendency to form products. When a reaction is taking place, the Gibbs energy will adjust itself to where it is at its minimum value. So the composition of the reaction mixture will continually adjust and readjust itself until the composition is such that the value of the Gibbs energy is at its minimum. Okay, so if we look at this graphically, looking at curve A, this curve here, let me see if I can find a spotlight. We look at this curve here. If we load at this on the y-axis is Gibbs energy. On the x-axis, if we go from the left, which is pure reactants, over to the right, which is pure products. So the left represents pure reactants. The composition changes, a mixture of pure products and reactants, mixture of products and reactants, all the way over until you have pure products. And then you look at what the Gibbs energy value is at each one of these, for each one of these curves. Curve A would be a graphical representation of a reaction that we do not expect to go very far. You can see here that in curve A, the minimum value of delta G occurs over here to the left. And on the left side, we know that this side is representative of mostly products in the reaction mixture. So therefore, since the Gibbs energy minimum occurs close to the left side, we would not expect that reaction to go. So that's why here it says reaction does not go. So we would expect in that reaction that mostly reactants are present. There's not going to be a lot of products formed. On the other hand, if you look at curve B, this curve here, we see that the Gibbs energy is at its lowest value around this point here. And if you look down here and see where that lies, it's about between pure products and pure reactants. So the Gibbs energy occurs at a minimum value between pure products and pure reactants. So we can anticipate that for this curve B, that we would have about an equilibrium amount where we have about the same amount of reactants as we do of products. This reaction would be one that would be pretty close to being at equilibrium. Looking at curve C. Curve C, the minimum value for delta G occurs right here. And that occurs all the way to the right on this axis. So therefore, the graphical representation for this curve tells us that we expect that mostly products would be formed in this particular graph or curve. So this reaction would be just about going to completion. So basically, this graphic just showed us how the Gibbs energy varies depending upon the type of reaction progress we can expect. It would look like this for a reaction that does not go and pretty much just is all reactants. the curve would look like this if we have an equivalent, approximately equal mixture of products and reactants. And it would look like this if we expect the reaction to go to near completion. Okay, so here are a couple of examples of different types of reactions, and I don't know why these arrows didn't come up right. But glucose 6-phosphate in aqueous solution going to fructose 6-phosphate in aqueous solution is an isomerization reaction, which is shown in your book. That's one of the reactions that they gave or provided as an example. Another reaction that they provided as an example for us to kind of study is nitrogen gas. This should be a small c. It should be subscripts. I don't know why they didn't come out right in the PowerPoint. Nitrogen gas plus hydrogen gas yields ammonia gas. And so no matter how the reaction is written, when we're talking about the reaction in its generic form, we can say that the generic way of writing a reaction is a reactant A plus another reactant B. And this little a is the stoichiometric coefficient. The big A is the actual compound. Yields a first product C. The little c is the stoichiometric coefficient. D is the other product. So this is the generic way of writing a chemical reaction. So basically, as the reaction proceeds, the Gibbs energy value for, or chemical potential for each substance is going to change by depending upon the change in the amount of substance that you have as the reaction progresses. And we'll look at that and what that means in the next couple of slides. Okay. So if this is our reaction, our generic reaction, we can write that the reaction Gibbs energy for this overall reaction is equal to 0 if this reaction is under equilibrium conditions. If the reaction is under equilibrium conditions, then the reaction delta G is 0. We know from chapters past that anytime we're talking about a thermodynamic quantity for a reaction, be it the reaction enthalpy, the reaction entropy, etc., we're talking about the value of the overall reaction for that particular quantity. So basically the value of delta G for that overall reaction for the products times the value of their stoichiometric coefficient minus the value of delta G for the reactants times the value of their stoichiometric coefficient, right? So when you sum up the products of, remembering how we used to do this, the sum of the stoichiometric coefficients of the products for delta G, of course. And this is going to be delta G, standard state, the delta G of formation, times the stoichiometric coefficient products minus the value of the reactants. And we're going to do some problems with this later on, but just remembering where the value for delta G reaction comes from. This value is pretty much equal to 0 at constant temperature and pressure when the reaction is at equilibrium. Okay, so what are the other meanings of the value for delta G? We already said that when delta G is equal to 0, We know that the reaction is at equilibrium. But what about when delta G is less than 0? When delta G is less than 0, then we expect that reaction to be spontaneous. And basically, we know that the delta G, which is on the y-axis, over the product composition, which is the delta N on the x-axis, delta G divided by delta N, when you take the slope of those two, taking the slope of that gives you the reaction Gibbs energy in this case. So looking at the first one where the slope is negative, the reaction Gibbs energy here is less than 0. The slope is negative, and we have a spontaneous reaction. So anytime delta G, delta reaction Gibbs energy, is less than 0, then we have a spontaneous reaction. We've already talked about this when the slope is equal to 1, or the slope is flat, and that means that delta G is equal to, delta reaction G is equal to 0, so therefore we have a equilibrium condition. And over here, graphically, we see that the slope is positive, which means that delta reaction G is greater than 0. So therefore, we have a non-spontaneous reaction. When delta G is greater than 0, the reaction going in this direction is not spontaneous. But as you can see, represented by this little arrow right here, it will be spontaneous in the opposite direction. Okay, so it wants to go back in this direction to where it gives energy as at the minimum. If you notice that at each one of these points, what these reactions are trying to do, it's spontaneous in the direction that is required to get to the energy minimum for delta G. So it's spontaneous in the direction that it will need to go in to get to the lowest value of delta G. Okay, so just one more time. Spontaneous when delta G is negative, equilibrium when delta G is 0, and non-spontaneous when delta G is positive. But when delta G is positive, then that means that the opposite reaction would be spontaneous. Okay, so how does the value of the reaction Gibbs energy vary with composition? We already talked about in the last chapter that we use the, we use the new term called activity to talk about solutes in solution. And we do that so that we don't have to worry about always comparing concentration or pressure and defining units for each one. We do that so it can be independent of whether we're talking about pressures or concentrations. So we're just simply talking about the activity of a solute in solution, and knowing that if it's a molar concentration, the activity is defined as the concentration divided by C naught. C naught is just 1 mole per cubic decimeter. And remember, we said that in doing that, if we have a concentration of some kind and we divide that by 1 mole per cubic decimeter, all that's going to do is basically, in effect, cancel out the units for our concentration and leave us with the unitless quantity, so that units don't become a burden for us when we're actually doing our calculations. The same is true when we have our sample or our solute expressed in pressure, where our pressure is expressed in the numerator, and then our P naught is expressed in the denominator, which is simply the value of 1 bar. And so if our pressure is in bar, then all that does is effectively serve to eliminate the units. And of course, for pure solids and liquids, the activity is always just simply equal to 1. So activity is pretty much the same thing as the concentration. Okay, just remember it's the same thing as a concentration, same thing as a pressure, except for we're just eliminating the unit so that we're not bothered with it. It's just basically like we said in the last chapter, it's basically like a fudge factor. It helps us to be able to just go in and fudge and just be able to just get rid of the units that we don't want to deal with. Okay. So I don't know what happened to this slide, but basically, if we're trying to find the reaction Gibbs energy, we have an equation here that allows us to do that. The reaction Gibbs energy is equal to the standard reaction Gibbs energy for that substance that we can look up in a table, plus RT times the natural log. If we have our reaction written in the standard form, remember that we said this is our generic form of writing the equation. Uh-oh. Okay, if we have our generic form of writing the equation, we can now say that in this parenthesis, we can say that RT natural log of the products raised to the power of their stoichiometric coefficient over the reactants raised to the power of their stoichiometric coefficient. So the activity, I've got to find a better way to write this without, okay. So the activity of C raised to the power of the stoichiometric coefficient of C times the activity or the concentration or pressure, whichever one, of D raised to the power of the stoichiometric coefficient of D over the activity of A raised to the stoichiometric coefficient of A over the activity of B raised to the stoichiometric coefficient of B. Remember, in general, you saw this as C raised to the power of C times D raised to the power of D over A raised to the power of A, B raised to the power of B. It's the same exact thing. You also saw this as pressure of A, of C, raised to the C, pressure of D, raised to the D, over pressure of A, raised to the A, pressure of B, raised to the B. Okay, now remember, the reason it's written like this now is because we were able to use the activity to say that it doesn't matter which one of these we're talking about. Doesn't matter whether we're talking about concentration, to write it like this, or pressure. It doesn't matter. We're just talking about the activity. Okay, so we can either be writing it like this or like this, and it is represented by the activity. Okay. All right, so since Q, remember our reaction quotient from general, Q is equal to both of these things, right? So basically, in P-Chem, Q is equal to the activity of C over raised to the power of C times the activity of D, raised to the D times the activity of A raised to the A times the activity of B raised to the B. So basically, this is the same thing as Q. So since this is the same thing as Q right here, we simply substitute this part of the equation for the letter Q. So our equation ends up being the reaction Gibbs energy is equal to the standard reaction Gibbs energy. Remember, this little circle here tells us that we're talking about the standard reaction Gibbs energy plus RT natural log of Q. Okay, so depending upon how the reaction composition changes, then that will tell you how your value for delta G will change. What does that mean, how the value of the reaction composition changes? Well, if the concentration of C changes, then that's going to change this value for the activity or the pressure of C, etc. And that's going to change the value of Q, which in turn will change the value of the reaction Gibbs energy. So depending upon how the products and reactants are changing relative to each other, this equation allows you to be able to calculate or estimate the value of the reaction Gibbs energy as a function of the reaction composition or as a function of Q. And so remember, Q tells us about the reaction composition at any arbitrary time, any time. It tells us about if we would just go at any point in the reaction and test and find out what is the concentration of the products and the reactants, and then calculate the value of delta G, then that will be using Q. Okay. On the other hand, if we do the same thing for the reaction when it is at its minimum value of delta G, and that minimum value is 0, then that means the reaction is at equilibrium. With this same generic reaction right here, then Q at equilibrium is the same thing as K. If you take this same generic reaction, the activity of the products raised to the power of the stoichiometric coefficients on the numerator, the activity of the reactants raised to the power of their stoichiometric coefficients in the denominator. It looks identical to what we just saw for Q. So at equilibrium, Q is equal to K. Okay. At equilibrium. Okay. Okay. At equilibrium, Q is equal to K. So I want you to always make sure that you keep that distinguished. Anytime in the reaction mixture, anytime that we sample the reaction mixture and we just want to know what the product composition is, we're talking about Q. If when we're sampling that reaction mixture and we're looking for what the product composition is and that reaction happens to be at equilibrium, we are talking about K. K is the equilibrium constant. Okay, and so your notes here tell you, although they look exactly the same in their equation form, Q tells us about the arbitrary position. K tells us about the composition when we're at equilibrium. When we're at equilibrium, we could set that value for delta G that we saw in that original equation a few minutes ago. We set that to 0. All right. So when we set that to 0, because we know that that is the value for delta reaction, for the change in reaction Gibbs energy at equilibrium, then we can move this over and solve for the value for the standard reaction Gibbs energy. So this equation now we can use at equilibrium. We can use it to find several different things. We can either solve for reaction Gibbs energy if we know what the equilibrium composition is. That means if we know what the concentration or the pressures, basically the activities of the products and the reactants are at equilibrium, we can then calculate K, which would then allow us to calculate the reaction Gibbs energy. Or if we know the standard reaction Gibbs energy, or if we know the standard reaction Gibbs energy for a particular substance or a particular reaction, we can then calculate the equilibrium constant from that value. So two different things that we can get from this equation. Well, from everything that we just learned on the slide. The first one is we can calculate the equilibrium constant with the same type of expression we saw for Q by understanding that it is only used when the reaction is at equilibrium. The second is we know that when that reaction is at equilibrium, the delta reaction Gibbs energy is equal to 0. When we set that value equal to 0, we can now solve for the standard reaction Gibbs energy if we know the equilibrium constant. If we know the standard reaction Gibbs energy, we can solve for the equilibrium constant. So those are the three takeaways from. So basically this is the same, just a repeat of what I just said. We can use the values of delta G, the standard reaction Gibbs energy from a data table to calculate K, or we can measure K or calculate K for a reaction using the equilibrium composition and calculate the reaction Gibbs energy. And we'll do problems like that, some sample ones in class. Okay. Okay, so now let's look at how the relationship is, what is the relationship between the standard reaction energy and the standard reaction Gibbs energy and the equilibrium constant. So if we know this is our equation, and we know that the natural log, when we rearrange that equation, we get that the natural log of K is equal to negative delta G naught over RT. So then you can estimate by looking at that expression that if delta G naught is less than 0, then the equilibrium constant is going to be less than 1. And that makes sense because we said that values for when delta G naught is less than 1, the equilibrium constant is greater than 1. So therefore, you should get a lot of products at equilibrium. At equilibrium, you should have more products than reactants. And the reaction should be thermodynamically feasible. That means that it should occur. If the value for delta G naught is less than 0, the value for equilibrium constant should be greater than 0. And your products should be more, at equilibrium, you should have more products in solution than reactants. And that reaction should be favorable. It should occur thermodynamically. On the other hand, if delta G is greater than 0, then that means that the equilibrium constant will be less than 1. And at equilibrium, you will have more reactants present. And the reaction will not be thermodynamically feasible. And this is supposed to be a superscript here. And so basically what this right here is saying, that those are what I just said. When delta G is less than 1, then K will be greater than 1. You will have products. Delta G is greater than 0. K is less than 1. You will have mostly reactants. Those are rules of thumb. Sometimes those aren't always the cases. And you can read your book and look at the notes in the next couple of slides that show you some of the examples of cases where you may not actually see that to happen. Okay, so these are some more intricacies of that equation. If we know that delta G is equal to delta H minus T delta S, and we're talking about thermodynamic favorability, we're talking about what has to happen to make the equilibrium constant be large enough for the reaction to be small enough. I'm sorry, what has to happen to make the equilibrium constant be large enough, or the value for delta G to be negative enough, in order that the reaction is thermodynamically feasible. So that means that by understanding how the values of temperature, entropy, and enthalpy change, then we can understand what the expectation should be for whether or not we can predict whether our reaction should be feasible or not. So here is a table that explains to us what those criteria are that allow us to be able to predict that. So if that's our master equation, delta G is equal to delta H minus T delta S, which we saw before. And if we're talking about reaction Gibbs energy here, then look at this table, and this table will show you all of the scenarios in which we can expect the value to be negative. Okay, so the first one, of course, is a no-brainer. If the reaction is exothermic, which means that the value of delta H is low, it's less than 0, which means it'll be a negative. And of course, the value of delta S then is greater than 0, then that means that both of these quantities will be negative. So that means, of course, we can expect that the reaction Gibbs energy will be a negative value. So basically, if we have an endothermic reaction and an increase in entropy, we can expect that that will be a thermodynamically favorable reaction. So therefore, we can expect our equilibrium constant to be greater than 1 at all temperatures, and that delta reaction, the standard reaction Gibbs energy, will be less than 0 in all temperatures. On the other hand, if both of these aren't favorable, remember, now if you start saying, okay, if delta S is not positive, or this is endothermic reaction, then you have different scenarios. So I want you to read those and understand those from your book and from these slides. This is the other extreme here, I guess, on the way out. If delta H is positive, so that means if this is an endothermic reaction and delta S is negative, which means that there is a decrease in entropy, that means that this is going to be a positive plus a negative times a negative, which is going to be a positive. So therefore, you have a positive plus a positive here. So we can definitely expect that in this case, delta G will always be positive regardless of the temperature. So that's the other extreme. The first example I showed you in the first slide was the extreme where both of them show favorability, and this one is the extreme where both of them show that the reaction is not favorable. It doesn't matter what the temperature will be. You will always end up in a situation where you have a positive value, multiply it by a positive value, and that will not ever be a favorable reaction. So this is pretty much the same thing. I don't know how that got in there. And these are, I think this slide just pretty much yeah, this slide pretty much is just a table that kind of succinctly summarizes the previous few slides. So just study the scenarios or the criteria from these slides here. Okay, these next couple of slides kind of got all messed up when they got on the program that I'm using, but basically these just pretty much say the same thing as that I said earlier on. I'm gonna move forward a little bit. I don't know how this happened, but let's just write what it's supposed to say. It's supposed to say that if we got the same generic reaction that we've been talking about, then we've got two different ways that we can calculate the standard reaction Gibbs energy. We talked about that at the beginning of the lecture. Okay. The first way is by the standard reaction Gibbs energy is equal to the sum of the stoichiometric coefficient times, say for the products, times the value of the Gibbs energy of formation for the products minus the value of the Gibbs free energy of formation, which basically is the amount of energy that is required for each compound to form from its elements, and that's looked up from a table. So just like all the others, okay? Okay, so I really hate writing on the iPad. It's not good. I'm sorry, but okay. So the standard reaction Gibbs energy is equal to the sum of the Gibbs energy of formation times the value of the stoichiometric coefficient for the products minus the sum of the Gibbs energy of formation for the reactants times the stoichiometric coefficient. And this is going to be not a delta here. Okay. Let me rewrite this to where it's more neat because it's kind of driving me insane. Okay. Gibbs energy of formation. Products. Okay, Gibbs energy of formation, reactants. Okay, the other way is we know that in order to get the Gibbs energy, you first find The reaction Gibbs energy. Sorry, we first find the standard reaction enthalpy, which you know is equal to the sum of the enthalpies of formation for the products. Let's go put a big P down here, minus the sum of the enthalpies of formation for the reactants. Put a big R down here. And the same thing is true for the reaction entropy, the standard reaction entropy. The sum of the molar entropy products times a product times the value of the stoichiometric coefficient minus the molar entropy of the reactants. You guys have seen this a whole bunch of times. Okay, so if you find these quantities separately, you can now come back and pop them into this expression is equal to delta reaction. Take the temperature and then multiply it by. So you solve for this quantity, solve for this quantity, multiply it by the temperature, and you get delta S. So this is something that you should have seen before too. Standard reaction Gibbs energy can be found by either using the first equation I showed you right here, by just simply plugging in the value of the Gibbs energies of formation for each individual product and reactant. Take the product times the value of the stoichiometric coefficient plus the other product times the value of the stoichiometric coefficient in brackets minus the sum of the reactant times the value of the stoichiometric coefficient plus the other reactant times the sum of the value times the value of the stoichiometric coefficient, and that gives you your overall reaction value for delta G. Otherwise, if you don't have those values, you can look up and calculate it indirectly by using this equation, because we know that delta G is equal to the enthalpy minus T delta S. We already know how to find the standard reaction enthalpy from way back. We already know how to find the standard reaction entropy from way back. So we can get these values from the back of the book, same exact way we did this. Stoichiometric coefficients times the value of the enthalpy of formation for the products minus standard enthalpy times the value of the stoichiometric coefficient for the reactants. Same scenario for the entropy values. Stoichiometric coefficient times the molar entropy values for the products, the sum of course, and then times the sum of the value of the stoichiometric coefficient times the molar entropy for the reactants. We'll do a problem like that in class on Tuesday. I'm going to skip through. I think this is going to be important at this time. I think we've already seen. Okay, so here's a table where some of these delta G values, the standard Gibbs energy of formation, can be found for different substances at 298 Kelvin. So if we were to do a problem where I were to ask you to find the standard reaction Gibbs energy, you would simply write your equation and come here and find your values for the standard reaction Gibbs energy. Okay, these are some of the values for your liquid solids. Okay, so let's put this into perspective about the standard Gibbs energy of formation. Okay, so think about the stability of compounds. If we look at the standard Gibbs energy of formation for different substances, and we imagine that the zero value here is sea level. Think about that. So that's basically our equilibrium value, 0. Think about anything that has a negative value, or in our imaginary below sea level, we can imagine to be stable and should not have any problems, you know, falling apart or staying stable. On the other hand, things like these compounds that are above our hypothetical sea level here are less stable, and they don't necessarily like to stay formed as the compounds that they are. So they are highly reactive, and they have a high propensity to decompose or to fall apart. Okay. Okay, I think this pretty much, I don't know how I mixed all of these slides up to say pretty much the same thing. Yeah, I guess it doesn't really necessarily say the same thing, but basically what this one is saying is that by knowing that the values of delta G can pretty much give you an indicator of the stability of a compound. If it's below 0, you know it's more stable. If it's higher, over 0, greater than 0, positive, you know it's less stable. Then therefore, you can pretty much use the value of of K, which is the equilibrium constant, to estimate whether you can expect something to be more or less stable, and whether something should have a tendency to form products or not. These numbers here should be superscripts. This PowerPoint got really messed up in the transition. Okay, so basically it kind of does say the same thing, but the only difference that this is telling you is that when K is much greater than 1, on the order of magnitude of about 1,000, then it tells you that you can pretty much estimate that the value for the standard reaction Gibbs energy should be about negative 17 kilojoules per mole. And if it's on the order of a thousandth, or 10 to the negative 3, then you can pretty much estimate that the standard reaction Gibbs energy will be about on the order of magnitude of about positive 17. So that's about the only significant difference in this slide. It just gives you a value that you can pretty much estimate based on what the equilibrium constant. Okay, so now how do we know, okay, thermodynamically we know that we can pretty much predict whether or not something should form products or not by looking at it graphically, by understanding what the value of delta G says, by understanding what the value of the equilibrium constant is. We have our equations for our equilibrium constant. We have our equations for determining the arbitrary concentration at any given time in a reaction. We have an ability to calculate the standard reaction Gibbs energy in 2 different quantities. So how would we go about calculating what would be the concentration of products and reactants that should be present at equilibrium? Okay, so we should remember this from back in the day. Your PChem book doesn't really go into providing a whole bunch of examples of this, so I'm going to give you 2. But basically, just to remind you of how we would use this information to calculate an equilibrium concentration is what we're going to do next. So I'm going to give you a hypothetical problem. what is the concentration of all species at equilibrium? Okay. What is the concentration of all species at equilibrium for the following reaction? If the equilibrium constant is 10 and the starting concentrations you have absolutely got to listen to what I'm saying when I read this problem because I'm not able to really write it very neatly because of the stylus. Okay, so here's the reaction. Okay, what is the concentration of all species at equilibrium for the following reaction if the equilibrium constant is 10 and the starting concentrations of each reactant are 1 molar? We're going to do a couple of these in class. So I'm just laying the foundation here to remind you of how we do this. So remember we have what we call an ice chart. So what we're trying to do, remember that we know that the equilibrium constant expression tells us that we've got products over reactants raised to the power of their stoichiometric coefficients, right? So basically, we're trying to find a way to use that expression that we can go back and solve for our equilibrium composition. And in order to do that, we set up what we call an ice chart, or a chart that allows us to be able to use our initial concentration, our expected change, and what we would expect to be a calculated change in the equilibrium. So our initial concentrations for each of the reactants are 1 molar. Okay, or we can just put 1 just to keep from, where we said these are activities anyway, so we really are not worried about putting our units in there right now. Right now, initially we have no product form, so the initial concentration of the product is 0. During the process, we expect to have a change to occur in the product side. We expect that there will be a decrease in the concentration of the reactants. So we say we're going to decrease by negative X, and this one is going to decrease by negative X as well. And this one is going to increase by X. So here's the thing. If this one, the N2, increased by X, then that means our H2 has to decrease by 3X. Okay, which is basically looking at the relationship of the stoichiometry to X. So here, our change here is X. Okay. Maybe I should give us a more simple one to start out with so that I can do this one for you in class. Let me give you a more straightforward one to start out with so I don't have to explain all of this here. I can kind of go a little bit more deeply into it in class. I shouldn't have to do that because I know you probably remember, but just in case, let's say hydrogen H2 plus I2 yields is at equilibrium. Remember, we have our double-edged, double-headed arrow here is equal to 2HI. Let's do it that way. That way I know that, that we're okay. So we can say negative x here and negative x here and positive 2x here. Okay. All right. So in equilibrium, what we would do is we would add these two things up. So adding these up over here, we get 1 minus x. Adding this up over here, we would get 1 minus x. Adding this up right here, we would get 2x. Now we need to write what our expression would be for the equilibrium constant, K. The equilibrium constant, K, for this particular reaction would be that the concentration or the activity of HI raised to the power of 2 over the activity of H2. We have no stoichiometric coefficient, so raised to the power of 1. The activity of I2. So when we substitute these equilibrium values into the equilibrium constant expression, we get 2x for the value of HI at equilibrium. And when we plug it in, we see we got to raise that to the 2. We get 1 minus x and 1 minus x. And so we know that the value for the equilibrium constant is 10. And so now what we would do is we would just go in and solve for our value of x and come back and plug it in here to solve for our equilibrium concentrations. Basically, what we have from the other slide is, let me see, 2x squared over 1 minus x. And anytime you have the same concentrations of starting materials or reactants, and this is our expression. So what we will be able to do is come in and do the square root of this. And what that will leave us with is 2x over 1 minus x. And then we can rearrange and solve more easily. But that's the math part. So you guys got that part, I hope. Okay. Okay. So we've already done this part in your earlier slides. So the last thing we're going to do is look at how the equilibrium constant is related. There's two different types of values for the equilibrium constant. We know that if we're talking about a gas, we can either express that gas in pressure or in concentration terms. We can express it in terms of the atmospheres, or the pressure or torr, or we can express it in pressure in terms of atmospheres, torrs, Pascal, bar, whatever unit of pressure that we would use to express a pressure quantity. We can also, if we know the size of that vessel, we can actually express that quantity in concentration. We can express a gas in moles per liter. So what if we want to look at the relationship between how the equilibrium constant for how the equilibrium constant varies depending upon whether we're expressing the quantity in concentration or pressure. Okay, so this is the relationship. If you see the equilibrium constant written like this for a gas, we pretty much can anticipate that it's implied that we're talking about Kp. If you see it written like this, you know we're talking about the equilibrium constant for the gas expressed in concentration. So the relationship is that the equilibrium constant expressed in terms of pressure is equal to the equilibrium constant expressed in terms of concentration times RT times delta N. And delta N is the change in the number of moles of gas from the product side to the reactant side. So number of gas moles of products minus number of moles of gas from the reactant side. So if you start out with the same number of moles of gas, what would you anticipate to happen to the value? If you start out with the same moles of gas and end with that same number of moles of gas, what would you anticipate to happen to be the relationship between Kp and Kc? If someone comes and tells me that, I'll give you 7 extra credit points. Okay, make that 5. I'll give you 5 extra credit points. So somebody come and tell me that without me asking you that question, and I will give you that extra credit. But the hint is delta N is going to be equal to 0. So what would you anticipate? Right? Okay. So this is our equation for that. And what we're going to do, we're going to end it here. So what I've done is I've gone through and I've given you an overview of your equations, of your concepts, of your basic fundamental theory of equilibrium. A lot of it you've already seen. Some of it is just a recap, which, we always say that all of your upper level chemistry will start out with a basic recap of something that you've seen in your general chemistry course, and then we'll build on it. But it started out at some point from the basics, and then we added a little. And what we're going to do is, I want you to take this basic information, synthesize it, understand it, and come to class. We're going to work some problems based on this basic, these basic concepts to reinforce those, and then you'll have your assignment after that.